Everyone. Thank you for joining this talk. My name is Gurjeet Singh. I am host of the IEEE Oregon Section Photonic Society. We are a new group. We are trying to arrange different talks for the people who are interested in photonics. And if you like to join and contribute to this society, you can do it with your Oregon section. Uh, our today's talk is enhancement in LiDAR SNR using non-classical light. Uh, we have with us Professor Amr Helmy. Professor Helmy is from University of Toronto, where he's a full professor. He did his MSc in 1995 and PhD in 1999 from University of Glasgow. He worked in Agilent Technologies from 2000 and 2004 and worked on various projects related to photonics like submarine class lasers and single mode lasers. For today's topic, he's going to talk to us about enhancement in LiDAR SNR using non-classical lights. So welcome, Professor Helmy.
Thank you so much. I really appreciated Ujit and I appreciated Naveen for the invitation. Very excited to be here and to be one of the early speakers in this newly formed chapter. So what I would like to talk to you about today is about some of the devices that are relatively mainstream, relatively practical, that you can package and put in a laser pointer type of form factor that can enable quantum technologies, particularly in the sensing. And I will use LiDAR as an example to show you how some of these technologies and devices can enable enhanced sensing by replacing classical light, like a laser, with quantum light. Before I start, I wanted to speak about the group. The team that worked with me is a group of PhD students, the ones shown in the first slide and the first bullet point. Han has contributed significantly to this work, and Bilal has contributed significantly to the devices side. Some of the initial spontaneous parametric time conversion work was done in collaboration with the University of Waterloo, particularly Professor Weiss and Genevine. Some of the phase-sensitive amplifier work was carried out in collaboration with Fujitsu Labs of America. The groups and the organizations within Canada that funded this work are NSERC, IDEAS, and ADSA. So what I would like to start with is an introduction. Why would we want to change the LiDAR that exists right now in autonomous cars and in many other applications with something that involves quantum light, which is usually seen as very delicate, loss sensitive, and not very practical. So initially, after I do this introduction, I'll speak about the devices. There's a very particular technology that we utilize that enables these systems to be fairly practical. And then after that, I'll take these devices and I'll deploy them, particularly in one example where quantum is used in sensing, and in this case, LiDAR. So at this point in time, autonomous driving has has provided an incredible demand on applications related to LiDAR because very high refresh rate, extremely uh, sort of images with extreme fidelity in 3 dimensions need to be obtained so that it can enable and it provides an input to accurate autonomous driving. So these are key at this point in time. Many companies have been working on this for the past 15 to 20 years, dozens upon dozens in the West and the eastern part of the globe. However, recently, because of the pervasive nature of these self-driving cars and the LiDAR itself, in some cases, will eventually will encounter some interference. Interference from what? Well, interference from other LiDAR. Let's assume we're going to a game in a stadium. How many cars will be there? So how many LiDARs will be working simultaneously? That's just one example. So from a noise resilience, there are still unmet demands for applications like target detection and LiDAR. But also from the hardware capabilities, the capabilities in the LiDAR itself have improved a great deal, but they still don't offer the noise rejection than what would hope to actually make it pervasive in very busy places. However, one attribute or one aspect that can help mitigate this noise challenge is to be able to operate these LiDARs at very photon flux, very low photon fluxes. So instead of whacking 100 milliwatts from every single one of these LiDARs in a square or a football game where you have 1,000 of these cars, no matter how eye safe it is, that would still be a challenge. So there is a demand for low flux imaging. And this demand for low flux imaging is not only in LiDAR. There are lots of target detection and imaging modalities that use classical light, such as LiDAR, like OCT, optical coherence tomography, and such, that demand very low photon level. Why? Because what it's imaging is live tissue most of the time, and this is extremely sensitive to photons. So you would like to be able to carry out the imaging with as minimal number of photons as you can. So there is a significant pull from some applications that require low flux, that require high resilience to noise, but there's also a push because now, as I will show you in the next 10, 15 minutes or so, the capabilities of entangled light generated from extremely practical structures that are electrically injected. It's basically like a diode laser, like the one that exists in a laser pointer, have become commonplace. So there's a push and a pull for such applications. So what are the devices that enable this quantum sensing, if you like? So what we do is we use very mainstream semiconductor lasers as the conduit, the basic building block for this quantum light. So let's just review for those of us who are not familiar with non-classical sources, what are the ingredients that are needed for classical sources to exist? So we need a nonlinear medium that has nonlinear interactions. So within these nonlinear interactions, we need to be able to have access to parametric processes. And for these parametric processes to take place, we need to be able to power them, empower them, and hence pump them using other types of photons or indeed current. And then you need means of engineering the structure, particularly its dispersion, to be able to engineer and tailor the state of the non-classical or quantum light that comes out. And when you achieve all these issues or all these goals, one is able to get non-classical entangled sources in many degrees of freedom. And in this case, the degrees of freedom can be anything related to the photon, its polarization, its time, frequency, momentum, all types of momentum, time bin, frequency bin, etc. So these are the ingredients that are needed for an entangled source. These ingredients usually exist in a system, an integrated circuit, an optical table, etc., etc. But what I would like to share with you today is how can all these ingredients exist in one diode laser. So our technology pivots on mature integrated optical technologies that are developed using existing, very well developed telecom type laser structures. So we've invented this technique. I've invented it when I first joined sort of academia after moving from HP/Agilent about 2005, 2006. So what is this? It's basically a laser diode that has a vertical structure that looks like a VCSEL, but light itself propagates along the direction of the layers, not across the layers. In this case, the beauty of the structure is that it has incredible control over the dispersion of the waves, and you can have analytical forms with these in 1D. Why is that important? Because you can have judicious design, extremely accurate, without doing numerical optimization in one dimension. Once you go to two dimension, then you need to use computer-aided design techniques like mode solvers and FTDT to fine-tune the effect. But the effect itself can actually be tuned almost from A to Z using the vertical direction. So this tuning can enable plenty of applications. Like if we can enable the width of the ridge, for example, in a 2D structure, we can enable the dispersion of the modes that are propagating inside of that edge emitting vertical cavity, if you will, to be zero. Dispersion could be zero, could be negative, it could be positive. This has a huge effect on the bandwidth of the processes that take place or come out of this structure. As an example, I'm showing you a table here that shows you the bandwidth of the entangled light that comes out, which is called the SPDC bandwidth, could go all the way from 100 gigahertz to 61 or 60 terahertz. That's about approximately 3 orders of magnitude, 2 to 3 orders of magnitude difference. That also follows suit in the temporal correlation between the photons that come out. So this level of versatility coming from just one laser diode chip is extremely interesting and powerful. So how do these devices work? Well, it's a structure that looks like a vertical cavity laser. You can pump it optically, so you can come in from the left-hand side here with the power supply. In this case, it's the red source, and it is the green source. And in this case, it is actually a power supply, but an optical power supply. And if you would like a parametric process to take place, you can end up inserting or injecting another light. In this case, the red pump. Sorry, the red signal. So in this case, the signal and the idler are uh, interacting together, and that's what is called a parametric structure or parametric process. Sorry. So this is how it would work if you optically inject it. But then you go further than that. If you electrically inject the structure, meaning if you actually emit or if you inject current vertically, just like you would do in a VCSEL structure, for those of us who are familiar with the VCSEL structure, you will find that you are able to inject positive and negative carriers, electrons and holes, and you will be able to get recombination in the quantum wells. These quantum wells can, with the right facets, laze. So you have the lambda pump lasing in the structure. So you have a lambda lasing in the structure. It will, by virtue of the parametric processes, generate a signal and idler right inside of the laser diode without injecting any light from the outside, just injecting current from a battery. And that's what we actually do. The current comes effectively from a battery. So what can one do with that? Well, one initially can mix frequencies. So you can build a laser like the one shown here, and the laser itself will have lasing light inside as a diode laser, and you can inject a certain color from the outside, in this case the blue wave, and this blue wave, by virtue of its color and the color of the pump, will generate the green wave, which will eventually, as shown in the spectrum, will follow the conservation laws to follow the change in the signal. So as you change the signal light, as shown in this animation, you will find that the idler light will change as well. So you can do frequency mixing just like what one does in some sort of a diode, right? While this is a very rudimentary parametric process, it's a process that usually takes place in an optical table or in a place that is relatively, or in a crystal. In this case, it is carried in a diode structure. So what else can we do? We can tune that parametric light to go not only around 1550, which is usually light that is useful for comms, but we can actually move to the near infrared, to the, if we pump at 1550, for example, and a signal at 1550 and the pump at 940, then we can get light around 2.5 to 2.4 microns. If we pump around 1530 and have a signal at 1900, we can get light that comes out around 8 and 9 microns. So that in and of itself is actually the longest wavelength generated from a guided wave structure in a semiconductor chip. One other notable aspect that these diode lasers can do is that can provide you with very unique amplifiers. If you look at the phasor diagram on the top left, you'll find that a typical amplifier in any domain, in the microwave, in the low frequency, in the HF, in the terahertz, and indeed in the optics, if you amplify the light, the circle here is denoting the noise that comes with that light. And if you amplify the blue vector with the noise associated with the blue sphere, then you amplify it to the red vector, and the sphere naturally will grow. So there is a rule of thumb. The standard quantum limit means that any amplifier, if it has a gain above 1, it will always have a minimum amount of noise that is 3 dB. So you will at least double the noise rather than anything else. There is another type of amplifiers that is called phase-sensitive amplifiers. And these amplifiers do something really interesting. Instead of amplifying all the noise in all dimensions in a sphere, it actually comes out with an ellipsoid, like the second graph. And that ellipsoid, it turns out, amplifies the light, and two components of it come with very different, extremely different noise attributes. So let's see if we can implement that. So we ended up building a device. While the Bragg device itself, the phase-sensitive amplifier, is shown here. And we launched a pump, which is the power supply, and we launched the signal itself, and we wanted to see, depending on the power of the power supply, whether that signal gets amplified or not. If you look at the signal amplification, you will find that the signal itself has been amplified in our devices, can be amplified if the phases of all the interacting waves are 0 or multiples of 2 pi, it can be amplified up to 30 dBs. Remember that these devices are extremely short, on the order of 100 micron. So if you are able to get a device, an amplifier that amplifies light in 100 micron, that is a record given the gain as a function of length. But what is more unique than that is that if you look at the noise figure of these amplifiers, because they are phase sensitive, you will find that the noise figure itself as a function of gain and hence as a function of input power goes down to zero, nearly zero. We could not measure it so exact. We measured it plus or minus a certain noise, and that noise could take it effectively below zero as an average, a mean value. But that just goes to tell you that we can have amplifiers that end up amplifying light with minimal to virtually no noise whatsoever. Such devices have huge implications in optical communication systems where nonlinearities and amplifier noise are the most limiting factor at this point in time, as well as in quantum photonics and quantum optics, where single photon devices could be amplified with minimum decoherence. So what else do we work on? Well, it turns out that these devices can provide not only interesting nonlinear processes. Remember that the initial slide that I mentioned to you, what are the ingredients for a good quantum source? Well, it turns out you need nonlinearities, parametric devices, and pump and dispersion. I've shown you ingredients that can control all these, but I only showed you how we can generate new nonlinear light. But I did not show you how we can use that to generate quantum light. So here in this part, I would like to share that with you. So it turns out that one can generate from these devices, if one pumps the right photon from the left right hand side here to the right hand side, one can generate different states of entanglement with with great degree of fidelity. So if you look at this particular example, for example, around the 1550, one can generate non-classical, entangled, indistinguishable sources around the 1550 region in the C band. But then this region can extend. If you tune your pump a little bit, the devices, the photons that come out non-degenerately. So every single color is the same photon pair. So the black and the black, and the red and the red, and the green and the green. And as you can see, the difference between the photons end up getting larger and larger. But their fidelity, how quantum they are, which is really the y-axis, does not change until they go beyond the C and around the end of the L band and the beginning of the S band. So that's a relatively large bandwidth for a chip that is basically just nothing but a laser diode. With more dispersion engineering, one can increase that bandwidth to become much more. And one can basically generate, for example, an entangled source that is entangled in polarization and compare it with a perfect theoretical entangled source or entangled state. And when you compare that theoretical comparison, you will find that this state ends up becoming actually almost perfect, almost basically within 96 to 98% resembling the theoretical state. And again, usually these states are generated routinely in physics labs and in some photonics labs, but usually on an optical table with plenty of fiber components and plenty of devices. Remember that this state is generated from nothing but a carefully designed laser diode. And that is a diode that can be battery operated, that can be placed in some sort of a laser pointer, if you will. So, okay, the laser itself, it turns out to be fairly unique as well, because this laser is based on a VCSEL, a vertical cavity structure, where the light is propagating laterally. So it turns out these lasers, when one is able to really control the dispersion in them, one is able to achieve great things. So let's look at a device where we have some sort of a satuable absorber, a section of the laser that is negatively biased, with two other gain sections that are forwardly biased like this. It turns out these structures can generate harmonic mode locking with pulses that are so short they were not generated or they were not measured before in a diode laser. So the shortest pulses that were generated from these devices, around 785 nanometer of emission wavelength, were around 130 femtosecond. Prior to this work, the longest pulses that were generated at that color from these lasers was the other extreme, the 743 femtosecond. So you can see there's approximately a factor of 5 or 6 reduction in the pulse rate as we are able to tune the dispersion and change the carrier lifetime of these. So that's a feat for the lasers themselves on their own right. Okay, so let me discuss with you right now some of the LiDAR, if you like, applications. So quantum illumination is one of the most exciting techniques that basically are used for using non-classical states, utilizing non-classical states of light for target detection. These techniques utilize two modes, two mode squeezed light to be to be generated and to fall on a target and to be compared with the reference photon at the output. And the setup to achieve all this looks like that. As you can see, yes, it's all fiber based, but mostly, not all of it. You will find that the OPA, the receiver, for example, is free space crystal. You will find that the source itself, which is the SPDC crystal, is also free space. So this, although it has the potential to be integrated in a fiber, it has still components of free space. But it turns out that one of the most inhibiting factors of using a technique like that, despite of it being noise resilient, despite of it being loss resilient, is that it requires every single interacting wave in the system to be phase coherent. All of them need to be absolutely and utterly absolutely and utterly phase coherent. That means that you can arbitrarily put the your basically your target and you know you actually have to leave it somewhere where you know exactly where it is within a micrometer of light. So there is another way to do this. Rather than using an entangled state and rather than being able to have a complete tomography of the state and take 10 minutes per pixel and need to know exactly within a wavelength of light where is the target, one can use quantum correlations. So it turned out that the entangled state of light involves a probe and a reference photon, two photons that come out simultaneously that are almost simultaneously generated, and the time between them relates to the lifetime of the state itself. So the detection time of each probe photon is random, but both of them come out together. That forms for an extremely effective way to filter these out. So how can that compare with quantum illumination? The quantum illumination technique that I just spoke to you about basically ends up simultaneously measuring the time and frequency coloration. It does tomography. It is intrinsically phase sensitive because it has some frequency generation interaction between photons. So the photons themselves all need to be phase sensitive, and it requires some sort of a quantum memory to be able to save one photon until the other photon goes, hits the target, and comes back. Okay, well, if one replaces that with another technique, such as the quantum temporal correlation LiDAR technique that we were discussing, one would only use temporal correlations to reject uncorrelated noise, and that serves as a simple, very low complexity filtering technique. This technique is phase insensitive because you do not need to have all the photons within a wavelength of light matched in their distance, and the measurable gain, if you like, is only dictated by the time resolution of the system, which in many cases is dictated by the time resolution of the detectors. So what do? We build a system like that and we compare it with others. We end up generating the entangled light here in the photon pair source. We end up separating the photons. One of them goes and hits a target. And when it falls down to the receiver, it actually has a measurable calibrated amount of noise and a measurable calibrated amount of loss. But the other photon end up going into a delay line until the source photon comes back. And we carry out the measurement that way. So when we carry out these measurements, we end up getting approximately a 20 dB enhancement in the signal to noise ratio, or the estimation basically ratio, when we use quantum light in comparison to using classical light. The challenge with using just temporal correlations like that is that this noise source, the noise source over here, if it has an enormous amount of photons compared to the quantum photons, the system itself will end up saturating. The detector is saturating. I'm sure many of us have seen a CCD camera that is not properly biased that ends up becoming completely white when you turn on the light. That's the detector saturating, right? You're not getting any intelligible signal. The same will happen for these. So what else can one use beyond just the simple temporal correlations, which still give us a low complexity filtering technique, but it does not really give us the level of robustness for, if you like, an imaging technique? Well, one can actually end up using temporal correlations on top of something else. What's the limit of temporal correlations alone? Well, the coincidence count and the receival will have a finite limit of rejecting noise because it basically, the noise flux will ultimately set the limit on the noise rejection. If you have a lot of noise, it will saturate the system. But the detection, uh, one can argue, is not completely quantum because you're just counting the coincidences. So how about if one uses another layer of quantumness on top of the nonlinear correlations? So what one would do, in principle, do a non-local effect, an effect that only takes place and manifests itself in quantum systems. So if you look at the state that comes out from a non-classical source, you will have a photon that comes out and gets reflected from a target, and let's depict it in the y-axis here, and let's have another photon that is basically the reference, which is depicted on the x-axis here. Because the entangled photons are entangled in time and frequency, the one of the photon pairs, which will go to the target, and the other one, which is the reference, are created at the same time exactly. So they see the same delay as each other, irrespective of what happens, because they're entangled, because of the time frequency entanglement. But what we can do is that we can pass them through different and opposite levels of dispersion. How would that work? So what you're doing really is that you're preserving the correlation, and you can see this as some sort of a fractional Fourier transform. But I'll discuss that later only if you'd like me to. It's only if you'd like me to. So what we do is that we generate the photon pairs, and we end up having a measured amount of loss and a measured amount of noise, and we get them to impinge on fall one of the photons to fall on a target. And what we end up doing is that we end up taking one of the photons and get it to go through a dispersion, positive dispersion fiber, and the other photon get it to go through a negative dispersion fiber. Well, we've just said that the probe and the reference, because they're entangled, they will always be at the same time, detected at the same time, so there will always be coincidences because of the entanglement. But then we are not only launching the quantum light here, we're also launching the noise. In this case, the noise will go through this positive and negative dispersion, and as it turns out, the positive and negative dispersion will really alleviate that level of noise. So if we have some sort of a dispersion cancellation, this will only happen for the quantum light, but not for the noise. So these are the different slides that depict the cancellation. What is the effect? The effect is that if you look at the amount of filtering that we get, if you look at the state at the output for the quantum light, it looks like the top joint probability plot. And if you have a frequency filter depicted by the red lines, you can only filter the quantum light. But if you look at the noise, because we went through positive and negative correlations, you will find that it will look like the bottom plot, which is the joint probability. That joint probability, as you can see, has spread significantly when you compare it with the quantum light. So if you deploy or employ the same filter depicted by the red lines for both together, you will find that the noise has been spread throughout the entire plot, and much lower amount of it sits within the filter. And that is an effective way of filtering using non-classical effects. So if you look at the signal to noise ratio of the system, if you deploy the quantum light, it's depicted by the blue plots, and the blue line is the theory. And if you look at the ones using classical light, it's depicted by the orange. Please note that the orange shows you a system where the classical signal to noise ratio is actually negative. So you're imaging in a system or trying to find in a target where the noise is approximately 100 times more than the signal. But if you switch and you remove the classical light and you put the quantum light, then you measure the blue line. The blue line tells you that this system, where the noise was 100 times more than the signal, now rendered you or gave you an image or a target with the signal being 100 times more than the noise. So there's about a 40 dB. In fact, we could measure up to a 43 dB enhancement in signal to noise ratio by switching classical to quantum and deploying this non-local effect that I described with the dispersion cancellation of quantum light on top of the temporal correlations. If you try to image a system using this technique, we try to image the images down here, U of t. So if you use classical light and you don't put any noise, figure C is the output, and you can still make out the U and the O and the T. If you add 25 dB worth of noise, then the classical light does not provide you with any intelligible signal because it gives you noise. But then if you use quantum light with no noise, it still gives you U and O of T. But if you use quantum light with noise, which is image B, you will find you could still, with some signal processing, be able to figure out the U and the O and the T. That's really like very simplistic, if you like, imaging, but it proves the point. There is an incredibly important, for LiDAR and radar, important metric called receiver operating characteristic. It's basically the maximal likelihood estimation of a probe transmission as the target detection signal. It just tells you what is the detection probability for a given false alarm. So intuitively speaking, if you want a radar, you would like the detection probability to be as close as possible to 1, for a false alarm to be as close as possible to 0, right? So you would like to be on the top, at the top of the y-axis when you are the closest to the leftmost part of the graph. And if you compare classical light, which is depicted here in black, with different variants of quantum light, using it in the same system that I just described, you will find that the system provides near unity, very close to unity, about like it goes only down to 50% of, reduction in the detection probability, while one is able to reduce the detection probability of classical light for up to 10 to the minus 9 false alarm, and the difference between them is over 60 dBs. So you can get an enhancement of over 60 dBs in that. It turns out there's also something very important related to quantum light. As I mentioned to you earlier, quantum light involves entangled photons that are generated at the same time. For any of us who've done electrical engineering and they've seen what a radar is, it depends on time of flight. You send a pulse and you time how long it takes to go and impinge on a target and come back, and then that time tells you twice the distance. It turns out, even when we use DC, like basically continuous wave, no pulsing whatsoever, because the entangled light has some time factors inherent within it, one can still be able to obtain ranging, but without pulses at all. And that is extremely important for LiDAR applications where you're trying to operate in a clandestine or undetected fashion. So there are lots of ins and outs and details relating to how one is able to actually detect a target. Here is an example of a target within a background of multiple points, if you like, of a screen, if you like, or sorry, a landscape of points on a screen. And one is able to, with quantum light and without quantum light, when we carry out this dispersion, one is able to, as depicted with the peak in white here, one is able to obtain a signal or a target in the nodes. There are lots of things that could be done beyond correlations. In fact, recently we've had some work that just came out recently where we can see the advantage between quantum and classical, not only on the order of 40 or 50 dBs like we showed in this work, but it can go up to 100 and 110 dBs as well. And that is because one is able to utilize quantum correlations relatively accurately, even with classical light. I think I'm going to stop here and I will just recap saying, and I discussed with you how one can use non-classical light from very practical sources to actually have practical modalities of LiDAR that does not require phase-sensitive, very delicate setup that can only work on an optical table. And I've shown you, or at least I've teased the opportunity of techniques with advantage of using quantum light that can go in the hundreds of dBs rather than just 30, 40 dBs that utilizes quantum light. it's very important at the end that we end up finishing this by saying the comparison between classical and quantum here, ladies and gents, always takes place when we compare like by like. So we always use the same number of photons to compare the performance in both. And because quantum light is usually extremely faint, it's usually like 10 to the 6, 10 to the 7, 10 to the 8 photons per second, where the light that you get out of a laser could be 10 to the 16, 10 to the 17, we still have to reduce the laser power of the classical LiDAR to be able to compare it with the quantum. In other words, if you have a LiDAR that has has infinite signal to noise ratio and have no challenges whatsoever in the signal to noise ratio, then you can probably never improve upon it using quantum. Only when you have a LiDAR system that is maybe limited in the flux, limited in the or limited by noise or loss or something like that, that you will really be best to utilize quantum. Thank you so very much for listening.
Thank you so much, Professor Helmy. That was a very interesting topic. Anyone has any questions? Nazneen, do you have any? Oh, yeah, Harish.
Sorry. I was coming in and out. Thank you, Professor. It was an excellent talk. Actually, very informative.
I really appreciate it, Harish. Thank you.
Harish, do you have any questions?
No specific questions. Actually,
Okay.
yeah, no specific questions.
Okay. Professor, if you don't mind, I have a few
Please,
questions.
absolutely. Yeah, take your, ask as many as you like.
Okay. So since you shown us the chip which has non-classical entangled photons as an output instead of a normal one, what's the range of that? Like how long you can detect that in a free space?
Oh, this is really dictated by the optics. We've done experiments up to 10 meters, but
Okay.
we've now been working on enhancing the flux of the quantum source, so we
Okay.
can go to hundreds of meters. And usually
Yeah.
LiDAR versus radar usually works around a couple of 100 meters. So we could do that still with quantum light. We just need to work on engineering the flux itself and increase it. That's an engineering problem rather than a physics problem.
Okay. Yeah. Uh, I worked on like single photon avalanche detectors, and some of
Yeah.
uh, the noise section, which usually I faced in those kind of systems, is like single photon avalanche detectors are really noisy. Like uh, with they have different kind of short
Because
noises, and then there's a
because
white noise. So does this
yeah,
system
because of the
help? Yeah,
multiplication noise, etc. Yeah.
yeah. And we were trying to scale up the resolution of that sensor, and that was a limiting factor. So does when we like again this I'm an engineer, so this is an engineering problem again. So in a
No,
non
absolutely.
yeah,
This type of approach
mhm.
actually does not end up helping you with the noise to the detector. But there are other quantum states that can help the detector go below the shot noise.
Okay, okay, yeah, that's interesting to know. Yeah,
Yeah.
uh
They're called squeezed states. They're called squeezed states. And these
squeeze
states can help
states.
you move, squeezed states. These can actually help you get a detector that is operating at the shot noise limit. You cannot make it any quieter than what it is. And it can actually take that system, like an interferometric system using that detector, and it can actually get you even better sensitivity. But I did not discuss that in this talk.
Okay, yeah, okay, thank you. Yeah, that answers my question. Thank you so much, Professor.
My pleasure.
Yeah, Nazneen, do you have any last comments?
I don't have any question, but thanks, Professor Amr Helmy, for coming, joining with us, and giving such an informative session. It was really awesome.
No, my pleasure, guys and gals, and I'm very grateful that I was one of the early speakers in the chapter. And let's keep in touch. Thank you so much.
Yeah. Thank you. Thank you so
Thank
much,
you.
Professor.
Of course.
Yeah.
Thank you. Take care.
Uh,
Bye bye.
bye bye.
Bye bye.